In this section, we'll take a look at the law of sines using side-side angle triangles. Let's try an example. In this example, we're being asked to solve the triangle with an angle alpha equal to 35 degrees, the side across from it, A, equal to 5, and another side, C, equal to 3. We're then asked to round to the nearest tenth. So I'm going to begin by labeling the items that have been given to us. Alpha is given as 35 degrees. The side across from it, A, is equal to 5. And C, another side, is equal to 3. All right, so what we have here is a side, and then an angle. So this is called a side-side angle triangle. And what you'll notice about this particular example is that we were given an angle with a side across from it. That creates that anchor situation that will allow us to use the law of sines. So specifically, let's remember that the law of sines says that if you have an angle and the side across from it, so in this case sine of alpha over A, that's going to equal the ratio of the sine of the other angles over the sides across from them. So those will all be equal. So I should be able to solve for gamma because gamma has the side given across from it. All right, so let's write that down. So I can say that the sine of gamma over 3 is equal to the sine of 35 degrees over 5. All right, and so I'm going to try and get that gamma by itself, but before I get the gamma by itself, I need to get the sine of gamma by itself. So I'm going to get that done by multiplying each side by 3, and that leaves me with the sine of gamma equal to whatever 3 times the sine of 35 degrees is, all divided by 5. Now, I don't always do this, but I'm going to put into my calculator what 3 times the sine of 35 degrees is divided by 5, and I'll show you why I want to do that. I get approximately 0.344. Now, the reason I want to do that is because I want to determine ahead. I just want to think about this. What could the possible gamma angle be? In other words, the sine of this angle gamma is equal to a positive output. And what I know is that that can only happen if the angle is in quadrant 1 or in quadrant 2. All right, so it's good to think about it because then when you get an answer, you can determine whether or not that seems reasonable or not. Okay, so now I'm going to take the inverse of each side. Take the inverse of each side. And sine inverse and sine undo each other. And so I am left with alpha equaling, when I put sine inverse of 0.344 into my calculator, I got approximately 20.1 degrees. And that is my quadrant 1 answer. So that seems like a reasonable answer. Now, what would the quadrant 2 angle be? We just got to make sure that that couldn't also be a possibility. Well, we need to think about reference angles, right? 20.1 degrees is its own reference angle. So in quadrant 2, using that as a reference angle, we could say that the other possibility for gamma would be 180 degrees minus that reference angle. And that gets me 159.9 degrees. Now, is that a possibility? Let's round that to 160 degrees just to make it easy for us. If gamma was 160 degrees, and I add that to the angle that was given, 160 degrees plus 35 degrees, that's 195 degrees. That's too big. Although it is a solution in this example with the triangle, it's not going to fit. So we can cross that out. All right, so let me mark in what we know. We know that gamma is 20.1 degrees. Okay, so now I could find beta, couldn't I? So beta is going to equal 180 degrees minus the 35 degrees that was given, minus the approximation of 20.1 degrees. And in all of these cases, by the way, I'm not actually putting in 20.1 degrees. I think the actual angle, what was it, 20.1 degrees. Let me look. I got 20.1296647.2. I'm using all of those digits so that I don't compound any rounding error. And when I do that and I round, I get 124.9 degrees. All right, so that's what my beta is equal to. There it is. So the only thing left that I need to solve for is the side that's across from beta, side B. Okay, so I'm going to say, let me just switch pens here and make a line. So I'm going to say that side B over the sine of the angle across from it is equal to, and I'm going to use my anchor. I always like to use what was given. So in this case, that would be 5 over the sine of 35 degrees. Now, to get b by itself, I'm going to multiply both sides by the sine of 124.9 degrees, and that's going to get me 5 times the sine of 124.9 degrees all over the sine of 35 degrees. And when I put that into my calculator, let's see what I get here. I got 7.152037118. Rounded to the nearest tenth, that's going to be approximately 7.2. So I'm going to go ahead and mark that on my triangle, and I think I'm done. All right, let's try another one. Solve the triangle where gamma is 50 degrees. Gamma is 50 degrees. Side A is equal to 8. And side C, which is across from gamma, is equal to 5. All right, so we've got that anchor, don't we? All right, now this, where we are given a side and another angle, is another example of a side-side angle triangle. So we know it's going to be a very similar process as what we just did. We're going to use the law of sines. And let's see here. I have my anchor, and then the other piece, side A, is across from angle alpha. So I think I'm going to try to solve for alpha first. So I'm going to write the sine of angle alpha over that side of 8 is equal to my anchor, which was the sine of 50 degrees over 5. I'm going to multiply both sides by 8. And when I multiply both sides by 8, let's just go ahead and write this out. I get that the sine of alpha is equal to 8 times the sine of 50 degrees all over 5. Now, 8 times the sine of 50 degrees divided by 5. Let's see what that is so we know what quadrant to expect our answer in. When I put that into my calculator, I got approximately 1.22. Now, what quadrant is that going to be in? I hope that you're saying to yourself right now, wait a second, that can't work. And if you're saying that, that's great, because that is correct. This one is not possible. Why is it not possible? Well, you can try it if you'd like. You can go ahead and put into your calculator sine inverse of 1.22. But when you do that, your calculator is going to scream at you error. Now, the reason why is because, maybe you remember, the range of the sine function, go back to your understanding of a unit circle. The range of the sine function is from -1 to 1. Can't be any smaller than -1, and it can't be any larger than 1. So having an output that's larger than 1, That's what's causing the problem. And we say that in this situation, no triangle exists. Now, you might be thinking to yourself, how can no triangle exist? I see a triangle right up there. On the next slide, I'm going to show you what that might look like. Okay, so here is that same example that we just looked at where we had gamma of 50 degrees, we had an A value equal to 8, and then C, of course, was the side across from it. And what you see in front of you is a video where I'm using a GeoGebra applet and I'm setting the given angle equal to that 50 degrees. The side across from it was 5. And then we knew that the other side that was given was 8. And you can see in this little image or this video that that side across from the given angle, it's just too short. It can't make it to that third side. And that's why in this scenario, we said that no triangle exists. No triangle exists. So using side-side angle, we have no triangle existing on this example. The example before this, we saw that one triangle existed. Let's look at one more example. So let's look at another example. In this example, we're being asked to solve a triangle where beta is equal to 15 degrees. The side across from beta, B, is equal to 6. And side C is equal to 10. And when we solve, we're asked to round to the nearest tenth. In this situation, we are being given a side and another side and an angle. And we know that that's called a side-side angle triangle. And we know that we can solve that using the law of sines. We have an anchor with the 15 degrees and the side length across from it of 6. So we are in business to use the law of sines. Now in this situation, we are also being given a side length of 10, which is across from angle gamma. So that's where I'm going to begin. And I'm going to write that the sine of gamma over side 10 is equal to my anchor, the sine of 15 degrees over 6. Now, I'm going to multiply both sides by 10. Multiply both sides by 10. Multiply this side by 10. 10s cancel out over on the left. And I'm left with the sine of alpha equaling whatever sine of 15 degrees is times 10 over 6. That should be multiplied by 10. So if I plug all of this into my calculator, I get that the sine of gamma is approximately 0.431. And the reason I sort of like to know that is because it gives me an indication of what that angle might be. I know that if you take the sine of an angle and you have a positive output, then that puts me in either quadrant 1 or it puts me in quadrant 2. And I know how to find both of those angles. The quadrant 1 angle is going to come about by taking the inverse of each side. If I take the inverse of the left, I'm left with gamma. And if I take the inverse of the right, inverse sine of 0.431, I get that angle gamma is approximately 25.6 degrees. And that is in quadrant 1, so that's my quadrant 1 answer. Now, to find the quadrant 2 answer, I need to remember how to do that. I know that in a circle, let's just sketch out a circle here, that if I have the 25.6 degrees over in the first quadrant, that sine of 0.431 is the height. That height is also over in quadrant 2. And the way that I can find that quadrant 2 angle is by taking 180 degrees. So I'm going to say or gamma is 180 degrees minus that reference angle of 25.6 degrees. And that gets me an angle measure of, let's see, 180 degrees minus 25.6 degrees is 154.4 degrees. Now, I know that that is an angle in quadrant 2, so that's great, but can that angle fit in the triangle? I already have 15 degrees. If I take 15 degrees and I add it to 154.4 degrees, will I have enough left over to have an angle alpha? Well, 154.4 degrees plus 15 degrees is 169.4 degrees. So yes, I would have enough. Not a lot, but I would have a little bit. So let's say this. Let's let the first gamma of 25.6 be called gamma sub 1. So if we have a gamma sub 1, then, so let's write this all out. If gamma is 25.6 degrees, then alpha sub 1 is going to equal the whole triangle minus the 25.6 degrees minus the 15 degrees that was given. So alpha sub 1 becomes, let's see, 180 degrees minus 25.6 degrees minus 15 degrees is 139.4 degrees. All right, so let me see if I can highlight this. I'm going to have if gamma is 25.6, then alpha is 139.4. Okay, if gamma is 154.4 degrees, then alpha sub 2 is going to equal 180 degrees minus the 154.4 degrees minus the 15 degrees that was given. So alpha sub 2 is going to equal, I think it comes out to be 10.6 degrees. And let me highlight that maybe in a different highlighter. So gamma sub 2 is 154.4, alpha sub 2 is 10.6. All right. So I think that the only thing we have left to find out is the side that is across from alpha. And of course, depending on whether alpha is alpha 1 versus alpha 2, then A is going to be different. So let me just put a line here. Let's talk about that. So if, let's say we're trying to find side A sub 1, then we're going to use the sign of alpha sub 1. And alpha sub 1 is that 139.4 degrees. Still going to set it equal to my anchor. So 6 over the sine of 15 degrees. And when I do that, and I'll leave the solving to you, I got that side A sub 1 was approximately 15.1. If I am looking for A sub 2, then I have to use alpha sub 2. So I'm going to put that 10.6 degrees in there. I'm going to still set that equal to my anchor. Set that equal to my anchor, and I'll leave the calculation to you. When I put this into my calculator, I got 4.24. So let me highlight again. When we had gamma sub 1 and alpha sub 1, then we had A sub 1. And when we had gamma sub 2, alpha sub 2, then we had side A sub 2. So we have two possible triangles. And how is that possible? On the next slide, I'm going to show you. So here's that example that we just looked at with beta equaling 15 degrees, the side across from it being 6, and a second side being given of c equals 10. So in this GeoGebra applet, I am setting the given angle to 15 degrees, the side across from it as 6, and then the side C, the other side, equal to 10. And notice there's one triangle, and there's a second triangle, and there's a first triangle again. So what's happening to create these two triangles, the reason it's happening is because there is no limitation on that top angle. That top angle can swing about. So in that type of situation, we can say that there are two possible triangles. Two possible triangles. And let's just identify what those triangles are. We might say that in triangle 1, we know that we have an angle alpha, we have an angle beta, and we have an angle gamma. And we know that across from those angles are side A, side B, and side C. Now, what was given was, of course, angle beta as 15 degrees, side B as 6, and side C as 10. Now, in that first triangle, I called the alpha, I called it alpha sub 1, and we found that to be 139.4 degrees. When it was 139.4 degrees, then the side across from it was 15.1. When alpha was 139.4 degrees, gamma was 25.6 degrees. Okay, triangle 2. Triangle 2, we still had an alpha, we still had a beta, and we still had a gamma. And we still had sides across from them, A, B, and C. Angle beta was 15 degrees, side B was 6, and side C was 10. Now, when we did it this way, our alpha sub 2 was 10.6 degrees, and the side across from it we determined was 4.24. When alpha was 10.6 degrees, then gamma sub 2 was 154.4 degrees. So two possible triangles in this situation. So when we're dealing with side-side angle triangles, we have to be careful. When more than one triangle may satisfy given criteria, we describe this as what is called the ambiguous case. Triangles classified as SSA and only SSA are those in which we know the lengths of two sides and the measurement of the angle opposite one of the given sides. In that scenario, we know that it may result in either one solution, meaning one triangle, two solutions, meaning two triangles, or no solutions, meaning no triangles. And here's how that could look. And I don't think that you need to memorize this information that's at the top, but I'm putting it on here. It's available to you if you would like to. But what I think you should always do is go through the process that we just did. If you're in a situation where you have to find the inverse of a sine and you get an angle measure, you always want to consider what could that other angle measure be and would that fit? If there's going to be no triangles, then that's this scenario A, where that side A in this case is just a little bit too short. Now, what's being given in the highlighted area is that the side A is less than h. What is h? You may recall that h was our altitude. So h in this case would be the perpendicular to this base. So you can see really clearly that that side A is shorter than what that altitude would be. So it just doesn't get there, and therefore you can't have a triangle. You would have a right triangle if A is actually equal to H. That would be a right triangle. And we didn't look at that example because we've talked about right triangles before. Let's go over to the one triangle situation on part D. That's going to be the situation where your angle A that's being given is larger, or excuse me, your angle A that's across from the given angle, that side is larger than the second side that's being given to you. And then there'll be two triangles when the side across from the angle that's given to you, the side that's across from the angle that's given to you is less than the second side, or if you happen to know what the height is, that perpendicular, which you probably don't know, but you could find out, if that side A is greater than that height. If it's greater than, then that's what tells us that it's going to possibly swing to the left and swing to the right.